Good afternoon, everyone. Are you guys ready for the exam on Friday? No? Well, hopefully today, after the review, you're going to be ready. I was planning that we go in order through every homework that you have done so far, and we'll finish with the last one, which is not too different from the one that you have already done. Okay, so let's do that. The first homework is homework number 6, okay? And for that homework number 6, I wasn't here, and I gave you a video instead, but we'll go now through the solution. All right. So the first problem is about stereo nets. And in that stereo net, what you have to do is to find what is the point that represents each of these faults with a given strike and a given dip. And here's the solution. Are you guys comfortable with stereo nets? So remember that for faults, it's not the same as for wellbores. For a fault, what you look at is at the projection of the stereo net on the, let me find another page over here. And I say it again because that's sometimes it's a confusion that I see in exams, and it's a pity for me to take some points off because of that, but I tell you that it happens. It's the same plot, but it's not the same thing for a fault or for a wellbore. Again, for a fault, usually, if this is a fault, this is going to be the strike, the dip is going to be in this direction, and what we plot in the stereo net is the pole. This is called the pole of the fault. It's a line which is perpendicular to the fault plane. And eventually what you put here in the stereo net is that projection. And you don't put the strike or where this intersection is on the lower hemisphere. I don't know if you saw my announcement, but I gave you directions about how to make this. Again, you can bring this to the exam. That's not an issue. Remember, for the fault is a perpendicular line, and that's a pole. For a wellbore, directly, since that's the line of the direction, we just plot the direction of the wellbore. So if we have a wellbore, for example, which is perpendicular to this fault, then that wellbore is going to plot also in the same location. If we have a wellbore which is parallel to the fault in the direction of the dip, then it's going to plot somewhere over here. Okay, so it is important that you know how to go from a strike and dip to stereo net, and also that you know how to go the inverse way from the stereo net through strike and dip. And in order to do that, for example, if I wanted to get the strike out of here, for example, from this one, all what you do is just you trace a perpendicular line. You may bring a ruler, that could be useful for the exam, and then a perpendicular line to it, and that's going to be the strike. And then you know that the dip is going to be in the other direction. Don't be fooled, remember? So this is the pole, then this is the line of the strike, the dip goes in the other direction. A question that came up during office hours, it was that if you need to know what is the representation of faults in geological maps. And I would say no, because we didn't go through that. But in part of my notes and in part of the homework solution, I use a symbol which is this symbol, and that symbol means that this is the strike, and it's dipping in this direction. And that represents the strike and dip of a fault. Here you can measure what the strike is, because this is, remember, always related to a coordinate system. But usually, if you want to know the dip here, you have to add that number. For example, for this one, let's say it is 50 degrees. You don't need to add that it's to the southwest, because you can already see it over there. For those of you that are thinking about what I meant with those geological maps, let me just go very quickly through that. But again, I'm not going to ask you questions about that. But it's something that you should know for your own benefit. And it is right here. This notation. When you step out of the class, if you take a look at this map over here, or if you're close to this map, you will see that same notation, how there is a little thing here on the side of the fault that indicates in which direction the fault is dipping. And it's on all of these faults. So it doesn't tell you what the dip is, but tells you what is the direction in which it's going. I think on the screen you cannot see this very well, but this is section 523, and there on your screen you'll see a lot better. Okay. Then I think now you're, from what you told me, you mastered stereo nets, so we can move on. And the next problem is about the ideal orientation of shear fractures and open mode fractures. And this is something very important that we need to discuss. Yes, Mr. Barake.
When you drew that circle for the wellbore location,
yes.
is that like if they said like, can you draw like the location of a wellbore on the stereo net?
It's not really the location of the wellbore, it's the orientation of the wellbore. It's not that the wellbore is like far from the center. This is just the orientation of the wellbore.
It goes along with the dip.
And?
Because it's going along with the dip.
No, I mean, for the wellbore it has nothing to do with the fault plane. It's something independent from it. Okay, so for then the next part, problem number 2 and number 3, they are very similar, and they ask you for ideal orientations of shear fractures and a hydraulic fracture. And that comes back to this plot over here, in which we have ideal orientations of shear fractures, and I didn't draw it in here, but also for what would be a hydraulic fracture. And for example, here the orientation of a hydraulic fracture would be perpendicular to SH mean, and that would have a strike of, in this case, north-south and dip 90 degrees. In this case, it's going to be the same. And in this case, it's going to be a horizontal plane. So there is no strike, and you just say it is a horizontal plane. But there is something very important to notice over here. On one side, we have ideal orientations, and on the other side, we have the real world and what has happened there with time. According to what we have seen here, is that if you have this combination of stresses and this state of stress, this stress regime, ideally these stresses should form fractures as you see them over here. And this is going to be with normal faulting, with strike slip, and we reverse. In ideal conditions, a normal fault is going to be relatively steep with an angle of about 60 degrees. A reverse fault is going to be relatively gently dipping with a dip of about 30 degrees. And a strike slip fault is going to have 90 degrees of dip, and it's going to have a strike which is not the same, while in the other two it is the same. And remember that this example is for SH mean acting on east-west direction. That might change. Okay, so these are the ideal conditions. However, sometimes in nature you can have a fault which is formed under this condition, but after 100 million years, stresses might change. Tectonic plates, they could move, and the stress could be different. So probably this, after 10 million years, if this side was going down, what is called the hanging wall, and the full wall was going up, after 10 million years, if the state of stress changes and it goes into reverse, this could change, and this could be reversed in the movement. So whenever I ask you about ideal orientation of fractures, I'm looking for what you would expect according to this theory that we have used, that according to the Moore circle, the angle between the angle of failure and the plane of maximum principal stress should be this angle beta, 45 degrees plus friction angle divided by 2. And that plane is going to move, or that side is going to move against SH mean or against S3 and in the direction of S1. That's it. That is the ideal. And if I ask you, for example, like in this other problem, let me find it. In this problem, what would be the state of stress that cause this type of faults? Then probably I forgot here to add the word ideal or the theoretical state of stress that would have caused those faults. But then that's also on the idea of this ideal notion of where fractures would happen. But again, with time, you could have fractures that are not oriented ideally or are not oriented according to the current state of stress. And that's why in nature you can have fractures in different directions in the same place that may not agree with the current state of stress. And that's what the following problem is about, in which you have faults at different orientations and you have to find out what is the stress on those. And they may not be in agreement with the ideal orientation because they might have been caused at different times. All right, so let's go by parts. Before I go to number 5, are there any questions about these ideal orientations of hydraulic fractures? By the way, again, you know, you're allowed to bring your set of cards. I also share with you the instructions to have these. But it's just very useful to remember that for this ideal orientation, the only thing you have to remember is that this thing, this cross, is the same as the sample that you failed in the laboratory, where the maximum stress was applied in this direction. So if it's a vertical load for S1, then this is going to fail like this, and hopefully you remember this shape. It doesn't matter if it's this way, that would be this card, or if it is that way, that would be the other card. Those are two possible solutions. Normally it's like this. Strike slip would be like that, loading from the side, and reverse would be something like let me find the orientation, there, also loading from the side, but now with the minimum principal stress in vertical direction. So the only thing you have to remember is, you can bring this one, you're welcome to do that, but you just have to remember this thing, how it fails, and that these two parts are going to move. Let me get the tape off. That these two parts are going to move, always opening or pushing against the minimum principal stress. In this case, vertical. In this case, horizontal. And in this case, horizontal too. And it moves in the direction of the maximum principal stress. Okay. Any questions? Yes.
So the dip of hydraulic fracture is either 0 degrees or 90 degrees?
Correct. Always assuming that SV is a principal stress. That's something that we have assumed for the entire course, and we'll continue to do that. But in real conditions, sometimes it might not be the case. But yes, under the assumption of SV is a principal stress, the hydraulic fracture is going to have a dip, which is either 90 in normal faulting and strike slip, or 0 in reverse. Okay, so the next problem then, problem number 5, is about finding what is the state of stress for 4 different faults within the system, within this problem. And for that, let me pull up the solution. Solution is here, and this one ends over here. It appears that that day the TA was not very awake because he missed number B, and he also didn't do correctly number 7 with friction angle equal to 1. So we'll get back to this, but let's go to number B. So I tell you what the solution is. Okay, so here's the solution again. You can do that at home. You can check it. And for this problem, basically what we're looking at it is a condition in which we have one stresses aligned east-west. So I can draw my block aligned with the coordinate system. This is north, east, and down. I'm going to convert these to effective stresses, so I don't have to write that much. The minimum principal stress is in direction east-west, and it's 40 MPa minus 20 effective is going to be 20 MPa. SH max is going to be 40 MPa, and SV is going to be, sigma V is going to be 25 MPa. Okay. And now the problem asks me to find stresses for these 4 faults. Okay. I'm going to solve this problem for the 3 or for the 4 faults in the same plot, but you could do it in different plots, and that's still all right. if I draw the 3D Moore circle for this, I'm going to have that these three values, so 40, 20, and 25. So let's put 40 here, 20 there, 25 over here. So this is going to be like this. That's going to be the Moore circle for that, where this is 25. And let's go to the first fault. The first fault strikes north-south and dips 60 degrees to the east. So something like north-south, 60 degrees to the east. Okay, so, and let's call this one number 1, or, yeah, number 1, let's call it number 1. In order to solve for normal stress and shear stress on this one, you have to see if, first of all, it is aligned with one of the principal stresses. And it is, it's aligned with this one. And the solution just depends on sigma V and sigma H mean. Let me add that over here. This is sigma H mean. This is sigma V. This is sigma H max. Okay. All right. And I know this is 65 degrees. So if I want to find I want to find where that is over here, I will have to use these two stresses, sigma V and sigma H mean, which are these two. So this is small Moore circle, and I have to go from the plane of the maximum stress, which is sigma V in this case, to the plane of the minimum, which is sigma H mean. So 65 times 2, then that's going to be 130. So that's going to be a point right there. That's number 1. And again, this angle over here is 2 times 65 degrees. All right? So you get the center and the radius of this, and then you can calculate that. Let's look at the next one, number 2. Number 2, it's a fault with a strike east-west and dips 35 degrees to the north. So it is something like this. That's a 35. And this one is number 2. If you want to locate that one in the Moore circle, I hope that you see that this one doesn't play any role at all. It's just a combination of these two, 25 and 40. So 25 and 40, then is going to be this Moore circle over here. And if you want to find it starting at this point, that's a plane of the maximum principal stress, which is going to be this plane over here. And notice, this is where it gets a little bit tricky. The angle that you need actually is not 35. The angle is the complementary angle to that, which is the angle from the plane of maximum principal stress, which is a plane of SH sigma H max, to the plane of the fault, and that's that angle, and it is 90 degrees minus 35, so 55 degrees. So when I go to the Moore circle now, that's going to be at the new center of the other circle. 55 times 2, 110, is going to be a point somewhere over here. That's number 2. Again, you get the center of that circle, the radius of that circle, and then you can calculate shear stress and normal stress. But again, a fractured rock mass can have fractures in many directions, some of them that were caused by different stress regimes over time. You can have rocks squeeze in one direction and then extend and be squeezed in another, so you could have very complex patterns of fractures in the same rock. Okay, and the third one is a fault with strike of 60 degrees and a dip of 90. So this is going to be something like this. Number 3. If you want to see where number 3 is in the Moore circle again, you look at the stresses that are going to be projected on that plane, and those are going to be the 2 horizontal stresses because the dip is 90, and therefore we're going to be dealing with the biggest Moore circle of the 3. The angle that you need now is always the angle from the plane of maximum stress, which in this case is 40. So in this case, it's going to be this angle. And we know that the strike was 60. So if this is 60 degrees, then this angle over here should be 30 degrees. And 30 degrees times 2, that's going to be 60. So from the center of this circle over here, that's going to be a point right here. And for number 4, finally, we have strike of 30 degrees and a dip of 25. So I'm not going to draw it in here because it's going to be a mess. But it's something which is, it has some strike and it has some dip. So something like this, where this is the north. And it's not going to be aligned with any of the stresses of the principal stresses, and therefore you cannot solve it. If you wanted to solve it, you would have to use this tensor method that you don't have to know how to do or how to use it, but you have to know that it exists and that it just consists about projecting stresses on the coordinate system of the fault. That's all what you have to know. And if you were to do that method, this would be a point somewhere inside here. Actually, I don't know very well. It would be probably, it's kind of difficult to figure out, but I don't know. I'm going to give a guess. Let's say somewhere over here. But I'm not sure about that, okay? But it's going to be somewhere inside the circle. In real systems, we have many times fractures in many directions. Most of them, they are organized systematically with some patterns, but sometimes not that much. But what you find in nature may not be necessarily what corresponds with the current state of stress. That's why it is important to get to know the state of stresses, to map all the current fractures, so you get to see if they are close to reactivation or not. The closer they are to this part of the Mohr circle or to the shear failure line, the closer they are going to be to shear reactivation. So then just to finalize this, if you compute tau divided sigma n, and if you compare this to the friction coefficient, then you can get to know if that's close or far from failure. Okay. Any question about this? Did any of you solve number 6? No? I'm sure you can do it. It's not difficult, but I'm sure you have other things to do as well. But again, you don't have to know how to do it, but it's a nice coding exercise that involves matrix multiplication and a little bit of linear algebra. Okay. And any question about that problem? Remember, very important, there are ideal fractures, ideal orientation of stresses corresponding to a set of fractures, but sometimes we have other fractures that may not be ideally oriented. I'm going to try to be very clear in the exam about what I am asking you, okay? All right, then if not, then let's do 7, and this is where I was telling you that there was a mistake, and the mistake is right. The solution for friction coefficient equal to 0.6 is correct, but probably you notice from here that the solution for friction coefficient is equal to 1 is the same, exactly the same, and that's not how it should be. In this case, the minimum principal stress for friction coefficient equal to 1 should be a lot closer to more or less than 60. And this one should be closer to something like 400. So check your own solution and make sure that you have the right one. This one is incorrect, okay? And other than that, this is relatively straightforward. Problem number 8, it's a problem that was discussed in class, and it is right here. In which, using the concept of equilibrium of faults or the limit of stresses at the point of failure at which you start to form faults, then you can calculate what is the minimum principal stress. And this is an alternative path to what we did with elasticity. Elasticity sometimes gives you a correct solution, but some other times it doesn't. And this other method can be very useful to define what is this type of stress. Question, also related to the exam and one of the practice exams. Forget about the actual value of stresses. How do you know that this is a normal fault? Yes.
Because you can see the hanging wall and footwall and the gravity and
And the hanging wall moves down relative to the footwall in every case. Hopefully you can get to see that. And this thing over here is what is called a graben. And sometimes when you have these elevated, let's say if we had something like this, this is what is called a horse. Again, that's geological knowledge. I'm not asking you to learn now in class, but you have to know the mechanics of those faults. All right, so are we good to go to wellbore stability? One more thing, before we go to there, this problem I like, I hope you all understood what's going on in here. You have the solution in Canvas, but these are all normal faults. This is a strike of the fault, and therefore this is something we don't know in which direction is dipping. It is like that or like that. Those two are possible solutions, but because this is normal faulting and this is the strike of the normal faults, again, we don't know the dipping here. Minimum principal stress has to be in this direction, more or less southeast direction, and therefore a horizontal wellbore should be oriented also in this direction. And let me just go very quickly through that. This is what Jeffrey obtained in the solution, where the north is pointing up. You can see the direction of the wellbores very much respects that regional stress orientation. Okay. Any questions about wellbore, about faults and fractures? No? All right, then let's go talk about wellbore stability. Do you have any questions about the homework number 8, I believe, and its solution? So this one is about calculating stresses around a cavity. I'm not going to ask you to do this in an exam. Don't worry, okay? You don't have to make these plots in an exam. But you have to know that stresses, the effect of variation of stresses due to the presence of the wellbore dies out very quickly. You can see here that almost like 2 radii away, 3 radii away, then you cannot see any effect of the stress anymore. And the other thing that you have to know is this amplification of stresses or variation from the far field values is the maximum at the wall of the wellbore. That's why we utilize these other equations with stresses at the wall of the wellbore. And you have to know also very well what's the hoop stress and what is the radial stress, and what are shear stresses too in cylindrical coordinates. Okay. The second problem, we talked about that one, and it basically consists on changing the value of pore pressure so that your mud window is going to change. And what I hope that you already did, and well, it's in the solution over here too. As lambda p increases or overpressure increases, the lines of PWBO and PV are going to cross. And let's see, this is the solution over here. This is what you see, PWBO and PV. There is a point in which if the pressure is too high, the wellbore may not be stable, because if you go below PWBO, then you have already an open mouth fracture. If you go above PV, then you have, if you go below PV, then you have significant shear failure. If you go above PV, then you will have quite a bit of a hydraulic fracture. So here in this region, it might be stable, but here it is not, because you cannot be at the value lower than PWBO and higher than PV. So everything over here is not stable. conceptually, higher pore pressure brings along lower effective stresses, which make the rock weaker, and that makes the drilling window smaller. All right, so you have all the calculations here. And I recommend that for some of these problems, and especially for this new homework that you're working on, you try to solve it by hand, okay? But then it may be a little bit tedious in some of these problems. I'm asking you to repeat this for several values. So you could do this in a spreadsheet, that's fine, or in Python or whatever you want, but just check it. Check one of those values, not everything, but just check one of those manually to make sure that you get the same number, because in the exam you're not going to be able to use a computer, okay? Yes?
Is your mud window whenever you convert your PW breakout to pounds per gallon and then up to your PV, or is it your PW shear?
It depends what you want. You may want a wellbore without breakouts. That's up to you. But that might not be feasible. So,
if you wanted one without breakouts,
so
you have to use the breakout one as your
yes. So in general, you go for a lower value that in which you do have breakouts, because otherwise your limits may be too. You might be too picky in designing your mud window. Say, I don't want any breakouts. You could do that, but you're going to end up with a very narrow mud window. So in general, you go for breakouts. That's fine. So you use PWBO instead of PW shear. Okay, and the last part of the problem, which is also very important, is, and it's also in one of the exams, is that if you're given a regional stress at a given location, that you're able to tell what is going to be the orientation of breakouts and tensile fractures. You need to know how to do this schematic, which is relatively simple, but you also need to know, if I give you a wellbore image like that one is kind of complicated, okay? Well, I'll give you a simpler one. If you see a wellbore image, how to recognize those breakouts and those tensile fractures. The breakouts, they usually appear as a thick wedge. Tensile fractures, they are thin, and they are very localized. And you will usually see that those are at the face of 90 degrees. Breakout, 90 degrees, tensile fracture, if any, 90 degrees, breakout, 90 degrees more, tensile fracture. If you have the image of a wellbore, you can also tell what is the orientation of the stresses. And that's the inverse process of that. Yes, Mishana. Yeah.
One of those, and you ask us to find the angle of the breakout. How do you do that?
Okay. So that's a good question. Let's see an example over here. So if I give you an image like this, probably I'll try to be specific and tell me what is the breakout angle at, say, this location over here where the mouse is. And I would expect that you give me this with a certainty of, I don't know, plus minus 20, 25 degrees. That's fine. I don't know what you see right now over here, but I know that from east to south there are 90 degrees. So this is more or less 45 degrees. So I would say the breakout, for example, at this location is about 50. If you tell me this is 10, then that's going to be wrong. If you tell me that this is 110, that's also wrong. But if you tell me this is 40, 50, 60, that's within the numbers I would expect. Also, it varies a little bit here and there. So I'll try to look for an easy example, but I'm just looking for examples in which you can more or less tell a value which is more or less accurate, but eyeballing is correct, or it's fine. Okay? All right, so, well, then that's all about homework number 8. And the one that you have to submit, I believe, today is homework number 9. And homework number 9 is quite similar to homework number 8, but now it involves other variables. And let me get there. I'll try to have this solution uploaded by tomorrow so you can study from it. Okay, problem 693. It's about exploring stress anisotropy for a vertical wellbore. And for a vertical wellbore, we're interested in the difference between sigma h max and sigma h min. That's a stress anisotropy. The bigger this quantity is, the more contrast of stress you're going to have around the wall of the wellbore. And what you're going to see in this case is that when you calculate your PWBO, I don't know why I'm writing sigmas. PWBO and your PB, these are going to narrow sigma h max minus sigma h min increase. So when there is small anisotropy, you may start somewhere over here. As anisotropy increases, it's going to be the same effect as the one with overpressure, and eventually there's going to be a point in which these two are going to cross each other. At that point, you might not have a stable condition to drill a wellbore anymore. So over here, this is going to be your mud window. It's very similar. Again, you can code these equations, but just check them at least once manually. Number 4, yes?
So we never have to solve for WBO, right?
You might have to do it, but if you do, I'll give you the equation.
But, okay, so like PWBO is obviously a function of WBO, but like, don't you usually, when you showed that graph, like don't you usually, or the wellbore image, usually just like see that, and that's what WBO is, or is there like someone you saw without?
Okay, so that's a good question. In practical terms, you may want to just set what is WBO and calculate PWBO, right? In some other applications, you may go and measure what the angle is. If you know what the pressure was, what the mass density was, and you know the properties of the rocks, you could get to calculate what is the maximum horizontal stress, which is something that we don't usually know. That's one of the few methods that allows you to calculate sigma h max or SH max. If you remember, we have seen how to calculate pore pressure, how to calculate vertical stress, how to calculate minimum principal stress, and we'll go more into this now when we start talking about hydraulic fracturing, but we never talk about SH max. How do you calculate SH max? One method is through the analysis of faults and equilibrium of faults, but another one is by measuring a breakout, and if you know the properties of the rock, you can get to calculate SH max. But in theory also, okay, so guys, we're out of time. Just let me tell you what goes on in here very quickly. 694 is just an offshore case, and it is very similar to what you have done before. Remember, please remember to know how to use lambda p, okay? That's how I'm going to give you pore pressure very likely if it's not hydrostatic, and how to calculate the stresses offshore and onshore. And 695 is just a case for horizontal wellbores, and you need to apply what you have learned before, but again by changing the stresses according to the plane perpendicular to the wellbore. That's all what you have to do. All right? Okay, guys. Please be here on time on Friday. I'll see you then.